Okay, people, let's get started. I'm going to use this mic up here for a while and not walk around because somebody pinched the lectern mobile mic over the weekend, so probably just walked off with it in their pocket. So what we're going to, this is a little ringy still. Yeah, I wanted to bring the volume down just a bit. It's ringing. Oh, there it is. Okay, so what we're going to do today is talk about extreme weather and the attribution of extreme weather. And it's almost the whole lecture. As I said last time, I'm about a lecture behind. That's pretty normal for me. And we'll make it up later. And the exam, more than 2 weeks from today, runs through not this Friday, but the Friday after. Whatever is accomplished by then will be what's on the exam. So, last time I talked about the difference between climate and weather. This is a really critical distinction. Climate is literally the probability distribution, or if you're a mathy person, the probability density of weather. It's a graph of how frequent weather events are of different severity, all right? And so if the weather were the numbers on a die, let's call them category 1, 2, 3, 4, 5, and 6 hurricanes. There is no category 6 hurricane, but that's only because the definition stopped at 5. We've had several hurricanes this year that would have qualified as a 6, and of course that right there should tell you that something funny is going on with hurricanes, or otherwise they would have developed a scale that went up to 6 to begin with. Why do we all of a sudden have a scale that would go to 6? The models that are developed here say that 7s are now possible, and we're waiting for 7. There actually was one that didn't hit land a couple of years ago in the middle of the Pacific, but these are getting up into the strength where the design criteria for tall buildings is violated, okay? The amount of pressure, wind pressure that a tall building is designed to withstand. And so that's actually, of course, concerning. You could imagine something like that hitting Miami and what that would mean, right? Anyway, so the climate for the weather of a die, if it's 1, 2, 3, 4, and 5, 6 hurricanes, would be that flat distribution there, where there's a 1/6 probability of each kind of an event. Now, of course, that has to be interpreted as given that an event occurs, because if it were really hurricanes, there's a high probability of no hurricane occurring at any one time, and a small probability of any hurricane occurring. And it turns out for real hurricanes, of course, 1s are more common than 2s, which are more common than 3s, which are more common than 4s, which are more common than 5s. But nonetheless, the important thing here is that the random event is the weather, and its probability distribution is the climate. And any probability distribution can be summarized by statistics. All right, there's a huge amount of information in a probability density or probability distribution. And, you know, the kind of things that summarize a distribution are its average value or its standard deviation and so on, okay? And so when we talk about climate, we're talking about statistics usually that describe a probability density, right? Okay, so bringing us relatively up to date, let's talk about 2 kinds of attribution. The first is climatological attribution. We know that some kind of an event is more common than it used to be in the past because of greenhouse gases we put in the atmosphere without trying to say which events were caused by them and which ones weren't. This is analogous to acquiring the statistics about increased accident risk from different blood titers of ethanol, okay? So how much ethanol did you drink? What's the amount in your blood? And then what's the probability of hitting people, right? And does the probability of hitting people having an accident go up with the ethanol titer in your blood? And the answer, of course, is yes, right? Up until the point where the person passes out and can't drive at all. Okay, so this report that came out just a month or so, two ago, has some statements that are first-timers for the IPCC report series, of course, that goes back now 30 years. First is that human-induced climate change, this is the banner number, is already affecting many weather and climate extremes in every region across the globe. Evidence of observed changes in extremes such as heat waves, heavy precipitation, droughts, and tropical cyclones, and in particular, their attribution to human influence has strengthened since the AR5. And by that they mean that in the AR5 they basically said it couldn't be done. Okay. And then 8.3.1, it is virtually certain that hot extremes have become more frequent and more intense across most land regions since the 1950s. Okay? So virtually certain in IPCC language means greater than 99% probable in scientific terms. 8.3.2 is that the frequency and intensity of heavy precipitation have increased since the 1950s over most land area for which observational data are sufficient for trend analysis. And that's high confidence. High confidence means large majority of the evidence. Decreases. Okay, so the next one here is that decreases in land monsoon precipitation, partly attributed. So this is a big deal because the monsoon is a big deal in Southeast Asia. If you're a farmer dependent on the monsoon, then this really matters. This one is less confident. It's medium confidence, but it still made the list. Yeah, okay, good. It is likely, that's more likely than not, that global production of major tropical cyclone occurrences has increased over the last 4 decades. All right, I'll show you some data, some of the raw data on which that is. Gonna turn that up? Okay, yeah. And so maybe, okay. So I'll show you some of the raw data from which that comes, and it's shocking, all right? The reason that's only likely is that there are so few really big storms. There are 90 hurricanes or cyclones every year that reach hurricane strength distributed around the world. A tiny fraction of those are major storms, and that's why there just hasn't been a lot of, haven't been that many storms. So here's the global surface temperature, and this might be the most primitive or most fundamental attribution statement that reconstructs the temperature record, for instance, over the last 2 millennia. And there's the current, okay? So it's clearly bounced well outside of the current, of the historic pattern that happened since the Ice Age. And there are some events here. There's some relatively interesting events, but you see that this is a pretty, it's just a remarkable departure. And if you put everything you know together about climate into a climate model, and except for the greenhouse gases and run the thing, it looks like this, okay? And if you put it together in a model and have the greenhouse gases, it looks like this, and the simulated range of uncertainty, given the amount of data we have gathered about the real world, is in the brown, and the black is the temperature record, and the brown is what's known as a multi-model ensemble. It's basically all the climate models of the world that are credible, put together to give you that multi-model ensemble, and the brown also reflects the differences in their predictions. There are wiggles in the mean of the multi-model ensemble. This is, for instance, Pinatubo. Mount Pinatubo goes off, and you expect to see a cooling signal, that sort of thing. But the point is that not only have we definitely observed something that is well outside the historic, what happened over the last 2 millennia, we can only explain this by looking at greenhouse gases. And scientists look for all kinds of other explanations, haven't been able to come up with any. And so, and beyond that, the evidence that it's actually greenhouse gases is itself multidimensional. It's not just the total mean temperature. It's the distribution of the temperature vertically and horizontally and through time, and it goes on and on and on and on. So in some sense, this is just a climatological attribution, right? That uses a model. That's the important thing. That also uses models. Doesn't just use data, it uses models. This says, geez, there's no doubt about it. The temperature is warmer than it used to be. I have detected a warming signal. And this says, given everything I know, I attribute the warming signal to greenhouse gases. Okay, and beyond that, you can attribute it much more finely, right? So this is the observed warming. That's the uncertainty in the observed warming, all right? So this is 2010 to 2019 relative to the last half of the 19th century. And you can see there that we've warmed about 1 degree Celsius, okay? And the total human influence, then, this is the attribution to all of the agents that we know about. The attribution to well-mixed greenhouse gases should have given us 1.5 degrees, but it didn't because the aerosols cooled us, all right? And you can break that further into the contribution from carbon dioxide, the contribution from methane, the contribution from N2O, the concentration from the refrigerants, and so on, and the cooling from sulfur dioxide almost exclusively, which is interesting because that comes from coal plants, okay? You'll see later that the solution to the climate problem involves almost certainly shutting the coal plants, the rest of the coal plants, over the entire, for instance, for the US, the entire United States, within the next 9 years. Just shut them all. And that'll just remove the US signal there almost entirely. And also, it'll save tens of thousands of lives almost immediately, all right? Because the fine particulate matter that kills people comes disproportionately from coal plants. So hanging on to them is a curious decision. In any case, the point here is this is also an attribution, not just to human influence, but also to the particular things that we're releasing. And this comes from a combination of physical knowledge, how radiative forcing works, and measurements, and models that propagate it through, and data, okay? And so there's a ton of stuff here. But the point is that the attribution is the result of a scientific process in the same way that attributions that we make in our daily lives, like ethanol consumption causes auto accidents if you drive, also requires multifaceted work, okay? Lots and lots and lots of multifaceted work. Now, the AR6 also shows that the data is now sufficient to start to do this on a more fine geographic scale, not just globally. And this is the sort of money figure on heat events, hot extremes. The dots indicate how much statistical confidence you have just from looking at the data about whether or not there's a trend. And the color indicates an increase or a decrease in the hot extremes. And what you can see here is that where we live, this is northeastern North America, there is quite high confidence, right, for just our region that it's gotten hotter. Interestingly, the hotbeds of where the most of the climate-denying public still disproportionately lives in the American South. and southern Midwest are spots where the signal is actually weaker. I actually don't think that's causal, but it is interesting that, that hot extremes haven't changed very much. Interestingly, a sidebar, hot extremes, if you measure them in terms of how sweltering the night is, what's the highest minimum temperature, daily temperature that you achieve? So it's 4 o'clock in the morning. It should be cooled down. What's the temperature? What's the highest daily low? All right. So that's the best indication of pre-air conditioning suffering. Okay, is whether or not you're laying in bed sweating, and those numbers have really changed in the American South. 4 of 7 nights now in the American South in summer are attributable, but these daily high extremes, which occur, early in the afternoon, show much weaker data, much weaker trend in the American South. This is the total change in heavy precipitation. You can see that heavy precipitation, in contrast, does show an increase, a statistical increase, and particularly here in Texas, all right, in Louisiana. They keep getting slammed, all right? I think Houston, anybody from Houston, from the Houston area? I think Houston has had 3 storms they talk about as 500-year storms, like in the last 5 years or something. It's like, that's either an unlucky streak or something's going on. So you can see that there are parts of we're starting to gather enough data and have enough of a time series to actually see the signal emerging at subcontinental scales. That's the point here. And this is agricultural and ecological drought. Drought, again, is something that is much less frequent than a heat event, all right, or even a heavy rainfall event. So it's kind of harder to pick up. You see that you're seeing an increase in Western North America, which, if you're from California, doesn't surprise you at all. And much bigger impact here across the Middle East and across Africa. So those are all climatological detections of climate change at subcontinental scales. But I want to talk about attribution of an extreme weather event to anthropogenic emissions. And remember, again, our analogy for statistical causality is going to be you drink to excess, you climb in your car, you hit somebody, and the state prosecutes you, and they win, okay? Because there's a legal definition of how high you can increase somebody's risk through your actions before you become culpable. It's considered causal, okay? And actually, the standard is interesting. It's more likely than not for lawsuits. It is more likely than not that you wouldn't have hit the person if you didn't drink. That's a doubling of your probability of hitting them. Okay, that's an increase of a doubling. So it was 50% less likely if you hadn't drunk. That's the tort standard. The standard in a criminal case is beyond a reasonable doubt. And it's not quite clear how to translate that into the sciences. And that's one of the problems. A scientist would say that that's a really stupid standard because, all doubt should be reasonable. The whole point is that you want to attack the edifice again and again and again. And you should treat every doubt as reasonable. There are attempts to try to say what this means. If you ask a legal scholar, if you ask a scientist what they think more beyond a reasonable doubt would be, they hedge, they average around 0.99, really high. Legal people and people from the humanities usually come up with a number that's significantly weaker, like 0.9, all right? But nonetheless, the criminal standard is a little bit trickier here. But nonetheless, there is one. I mean, make no mistake, otherwise, if you drink to excess and hit somebody, you don't get in trouble, right? All right. So now we're talking about what happens if you roll a 6. Can we say whether or not rolling a 6 has changed? Has somebody been fiddling with our die, right? That's what we're talking about. So 6 years ago, it was impossible to do this, all right? Most of the methodology to do this has been assimilated into the mainstream of the scientific community within the last 6 years. And so now it's possible to attribute many different kinds. So here's sort of what's going on here to some extent. Definition of extreme. So here's a probability distribution. This is a normal probability distribution, the kind that you've seen, the bell-shaped curve. A normal probability distribution turns out to be lousy for weather. Our intuition is shaped by normal probability densities if you're a scientist or engineer. And it turns out it's a lousy model for a reason I'll talk about in a minute. But nonetheless, if it were normal, there are these events out here in the tails, which are extremes, okay? And so you can imagine that climate change, greenhouse gases, would have shifted the distribution of weather severity here to the right. That's heat. That means that on average it's hotter. But see, the tail here of this dotted distribution is now thicker, taller, than the tail of the other distribution. And the area under the curve between two values is the probability that there would be an event in any given point in time between those values. And so you can see the area under the dotted curve out here is much bigger, like double the size of the area under the solid line curve. And those two are two probabilities of experiencing extreme weather, like two probabilities of hitting a pedestrian with and without alcohol in your blood at the legal limit, okay? So that's what's going on here. And this is a climate, and a place on this axis is a weather event, okay? So you could imagine you would also get a change in the extremes from an increase in the variability. There isn't very much evidence that there's a lot of that going on in the climate system. And you could also get it by a change in the symmetry. This thing just kind of, changing its shape a little bit. But we're going to kind of focus on changes in the mean because it looks like that's mostly what's going on. It's just that the distributions aren't bell-shaped. More on that in a minute. So two kinds of extremes. Frequency. The frequency of an extreme event is defined as, well, you can define frequency as the return time. How many years do you have to wait between events of a particular severity? So if it's, middle of the summer and it's 115 outside, and you think, holy smokes, that's hot. How long do you have to wait to the next 115-degree day on average? The shorter that interval is, the hotter, the more frequent the extremes are. So that's daily precipitation exceeding P centimeters, seasons with less than R centimeters of rain, wind speed in X of W kilometers per hour. It just goes on and on. You can do this for anything, all right? That's frequency. And severity is a measure of the severity of some extreme, like the hottest or coldest temperature in a particular period, like within a year, within a decade. The highest one-day precipitation within a century. The driest summer or the highest wind speed in Y years, all right? So frequency is the amount of time you got to wait between events of a particular severity, and severity is the most extreme, is a measure of the most extreme event you have within a particular time frame. All right, so these are very specific definitions that don't correspond to the English, sort of standard English definitions of these words. So you really want to pay attention that there's a difference here. There's a precise technical definition here. Okay, so how do we measure the elevated risk associated with climate change for a particular event, okay? So imagine that the blue is the distribution of the climate, say maximum daily temperature in degrees Celsius within any year. What's the maximum temperature in degrees Celsius in any year? And let's suppose blue is the distribution of those maxima, or let's suppose that's maximum daily temperature, period, just period. Actually, for this graph, it's got to be, because it goes down to -20, okay? So that's like on any day, given the weather, you go look at a century's worth of data, what's the maximum daily temperature and the minimum daily? How frequent are they? And blue is the pre-industrial climate, maybe from data records. So occasionally there are 40 degrees Celsius days, and occasionally there are minus 20s, and the average here is somewhere around 10 degrees, okay? And then we look at the distribution, say, since 1950 for some proxy for the current climate. And so let's choose a particular hot threshold. Call it 40 degrees Celsius, right? Nice hot day, 40 degrees Celsius. It's 100 and something in Fahrenheit. And let's call the probability of its occurrence P40, okay? P40 here. Now, you'll notice that to get at this, you go down to 40 degrees and then over to this axis, right, in the pre-industrial climate, and then you read this value off, which is about 0.002, or about 2/1000ths of the days. Do you have a temperature that high in the pre-industrial? That's what that means, okay? 2/1000ths of the days. You do the same thing in the current climate, and you can see that we've got about 6/1000ths, about 6 days in 1,000, or 2 per year do you hit 40 degrees Celsius, okay? Under the current climate. And we'll call that P40 today. So the measure that people use for the change in the frequency is called the fraction of attributable risk. And its formula for this 40 degrees Celsius extreme is 1 minus the pre-40 of the pre-industrial, which was 0.002, over P40 today, which was 0.006. And if you do the arithmetic, that's 2/3. That is, if you're standing in a 40-degree day today, sweltering in the 100 and some degree Fahrenheit heat, and you say, how likely is it that this day was caused by climate change? This answer says it's 2/3. That should be intuitive to you because the frequency today is 0.006. It used to be 0.002. It's tripled the frequency, which means on average, 2 of 3 events you experience today are going to have been caused by the rise in their frequency, right? That's what that thing does. So that's a fraction of attributable risk. And you can do the same thing for the magnitude. You can take an event occurring at a particular frequency. In this case, I've chosen 0.0009, which means once in 1,095 days, or once every 3 years. Okay, so the frequency here, the return time we're talking about here in the pre-industrial is 3 years. All right, we're going to look for an event that occurs only once on average every 3 years in the pre-industrial. And there it is. And we'll look then at the size of that event, where the once in 3 years line crosses the probability density, the climate for the pre-industrial. And you can see that's just about 39 degrees Celsius. All right? So that's a 1 in 3 year event in the pre-industrial. You do the same thing for the current climate, and you find out that the answer is 45 degrees. Okay? 45 degrees. The fraction of attributable magnitude is 1 minus this magnitude for the once in 3 year event in the pre-industrial over the magnitude of the once in 3 year event today. And you do the math, and you find out that that change increased the frequency of or the severity of the magnitude of a once in 3 year event by about 13%. All right? So you can attribute statistically, in a probabilistic sense, both the magnitude and the frequency. Frequency is used much more commonly than the magnitude. All right. So these two measures, I expect you to know those definitions, but I'm not going to have you just like calculate stuff all over the place. This is as bad as the math gets in this part of the course, at least. So the fraction of attributable risk and the fraction of attributable magnitude can also be defined over other periods, such as, for instance, the 1960s versus the 2000s. All right? And so you use the same thing instead of doing it in the pre-industrial and today. You use it for 2 different periods, and you then simply ask, how much does the climate change over the last, in this case, 50 years, caused an increase in the magnitude or frequency of some event? And if we can apply statistical methods to this, and if we can show that this is a statistically significant change, then we've done a detection of an individual event. We've detected that it's more frequent, for instance, or more severe. And you can also do this with climate models. There's like a lot of blah, blah, blah on this screen. But the important thing is we've got today's data. We know the models can warm up till today. And so the models can be used to create and reproduce what we see today. And so we can look at the models to say, well, what would today have been like if we hadn't put greenhouse gases in the atmosphere? Or if we hadn't put just the N2O in the atmosphere, or any counterfactual we want, if we hadn't cut down the forests, right? And so then what you're looking for is the fraction of attributable risk for the difference between a counterfactual world and today's world, in the same way we did it before for the pre-industrial world versus today's world, okay? Counterfactual world. And it's the same formula, 1 minus P counterfactual over P today, 1 minus M counterfactual over M today magnitude. And you can do statistics, the same thing, and if you see a significant effect, you say, you know something, I've actually attributed a change to some factor, okay? So for our drunk driver, this would be probability of hitting somebody with and without ethanol, right? If you had and so you're attributing it to ethanol, as opposed to other prescription drugs that person might have been taking, that sort of thing. Okay, so this has started to be used relatively recently. The first study was in 2003, and there was a European heat wave that killed 35,000 people. It's been superseded now, and a bunch of these characters, Peter Stott, D.A. Stone, and Miles Allen, came up with a fraction of attributable risk above 0.5. And this kind of stunned people because they're like, whoa, we've actually seen an event that beat the legal standard for a lawsuit for torts, okay? There's more than 1 chance in 2, they thought, that this event wouldn't have happened had there not been greenhouse gases put in the atmosphere. The IPCC, last time around, the AR5, looked at temperature extremes like the return time, the coldest night that occurred in 20 years. And this graph, you can read this at your leisure, is about the coldest or the hottest daytime or nighttime in 20 years. And there's a bunch of stuff they found out that was really pretty interesting. So in the 1960s, for instance, this shows, is that the hottest nighttime low in 20 years, so that for the hottest nighttime in 20 years, the most sweltering light in the 1960s, if you waited till the 1990s and said how frequent is it, it occurs once every 8 years already. So it's more than doubled in frequency, right? The return time has more than halved from 20 years to 8. And so there was actually a surprise when they assembled all this data worldwide that you were starting to be able to see really big changes occurring just over a period of a couple of decades, right? So this is a 30-year change that more than doubled a sweltering night. And you can look at this, they did it for different continents, and there were just signals all over the place. And that really spurred a lot of interest in trying to do this for specific extreme events. And everybody kind of got into high gear about 5 or 6 years ago. Turns out, so people started doing this. The organization that organized it is actually headquartered here in Princeton. It's a climate communication organization called Climate Central. It's on 1 Palmer Square, I think on the 3rd and 4th floors there. And they actually spearheaded this, organized the scientific community to do it, paid for a lot of the work, blah, 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 right? And so a lot of it developed, and everybody was astonished at how big the signals were. And the reason the signals are so big is that the distributions aren't normal. they're curtailed. You see how abrupt these things are. This thing looks kind of squarish, all right? Not like a normal bell-shaped curve. And the reason is that the tails get chopped off really quick. And they get chopped off because, like, for instance, if it gets really hot in one place, it sends up a big temperature gradient between that place and surrounding places, and then the wind starts to blow as a result and mixes up the atmospheres. So the physics pulls extremes back to the middle. For those of you who are into this sort of thing, this is not necessary. A normal distribution comes from something in which there is the sum, literally the sum, of a whole bunch of random factors that are added together. There is no force. They're independent random factors added together. There's nothing in a normal distribution or the processes that generate it that pulls things back towards the mean. And so the tails can get really long, but it turns out they're really chopped off for a lot of the events that we're talking about here. And that means that over this region, for instance, this amber curve has substantial probability density for a rare event that you never would have seen in the blue. It's just like infinitely more likely because of the chopped off tails. If those things were actually square waves, right, just bars, then the climate as the mean changes carves out new territory that have never been seen before. All right, so that's why. So the National Academy of Sciences, which is the premier group to review stuff like this in the world, came up with a review that they released in March of 2016. And they said, you know something? It's actually possible to do this now. And so they identified heat waves and coastal flooding as two that you could do it for, and hurricanes and tornadoes as something for which you couldn't do it for. And that's 5 years ago. And then they forget about this slide. Cross it out in your notes. There's a huge literature that developed. The Bulletin of the American Meteorological Society published a special report every year that looked retrospectively at that year's extreme events and ran these kinds of analyses on them and attributed things. They looked at 131 events over 6 years, and 65% had an anthropogenic effect. They did an attribution. So the weather really does seem weird for a reason. 2/3 of the ones they looked at were for real. There's been a new compendium just in the last couple of months, actually the last month. By 2021, last month in 2021, there have been 350 peer-reviewed studies in total now. And 70% of the 405 extreme weather events examined were found to be made more likely by human-caused climate change. 9% were made less severe, and so that 79% overall had some human impact. And a less severe event would be cold waves, right? Extreme cold is less common, so it's more mild. The remaining 21% of events showed no trend. 92% of extreme heat events were found to have a climate change signal. 58% of extreme flooding were found to have a human signal. So that's kind of where this is now. There's a whole bunch of other stuff on here. The IPCC says it's virtually certain, remember, that the frequency and intensity of heat waves has shot up. There does not appear to be a distinct global or regional trend in the number of tropical cyclones known as hurricanes. There is one for their intensity. I'll show you that later. And the IPCC, remember, said that. We have these rapidly intensifying hurricanes, but they don't appear to be coming more frequently, all right? The data don't show any increase overall in the frequency, just the severity. The World Weather Attribution Initiative that was actually funded by this NGO over here on Nassau Street is an international consortium that's been trying to speed up the time to do this. And so they've now gotten the time down to about a month, 2 weeks in some places. And they found, for instance, that the heat wave this June, remember, the British Columbia and Pacific Northwest heat wave, that unbelievable heat wave that happened this summer, that was, they think, impossible without the climate having been a change. That's a fraction of attributable risk of 1, all right? They did that rapidly. The idea is that you get the news hook when the event's happening. Once it's over, everybody kind of forgets about it. And you heard it here first. They haven't announced yet, but they've completed the massive cooperative computational exercise to issue same-day attributions. They've got a capability that's going hot to do this for heat everywhere in the world, every day, for every forecast also. And so there are discussions with Apple and IBM, which is weather.com, to get a fraction of attributable risk on your iPhone, right, or on your phone, right? So when you bring up a weather app, if it shows what the temperature, high temperature was today, it might have a little number there, like 1.5, right, which is a fraction of attributable risk, right? Or 2 would mean it's twice as likely, right? So expect to see that once those negotiations are complete, but they've got it down to where they want it to be, which is when it's happening and attributing the forecast if the forecast were to come true, all right? So blah, blah, blah. There's a bunch more of these. A bunch more of these where they're increasingly seeing events that would have been impossible without this. Like it got to 100 degrees Fahrenheit north of the Arctic Circle in Siberia. Right? That was impossible, they think, without it. So there are a lot of events, like I said, I think last time or in one of the other lectures, where the frequencies are going up and where the attribution is really strong. Most floods now on the coast are human-caused right now. Okay, that's in the United States, eastern United States. If you have coastal property in the eastern United States, it's in trouble. 76% are human-caused. The Great Barrier Reef died a couple of years ago, 90% of it. That event, a hot water event, had a fraction of attributable risk in excess of 99%. Actually, the return time, they thought, of the actual increase in frequency was over 2,000. Hurricane Harvey's rainfall, about a month after it happened, or maybe 2 months after it happened, there were some early studies that found a fractionable of attributable risk as 2/3. That's, of course, high enough for a lawsuit. And I will say that, I talked to a judge who is responsible for this sort of thing, and they've been absolutely inundated with lawsuits by people whose house got knocked down because the Houston Water Authority people had to open floodgates to reservoirs because they were overwhelmed. And the question is, why didn't you anticipate this? All right? The scientists were telling you, for political reasons, you denied the science, and now you, the city of Houston, have to pay for my house, which you knocked down. There was another study of Hurricane Harvey that came up with almost the same number, 0.71 versus 0.67. There are events like Arabian Sea hurricanes that were never seen, and then there were 2 of them in 2015 with fractions of attributable risk of 0.64. The models now indicate that the hurricanes can go into the Persian Gulf and wreck the oil infrastructure there. And it turns out that none of it is designed for hurricanes because they never have occurred there historically. Gabe Vecchi actually is here at Princeton. He's the new director of the High Meadows Environmental Institute. Here's the data on hurricanes. I find this horrible. This is the current increase in the frequency of hurricanes since 1980, and this goes up to 2016. And so Category 2 hurricanes and lower haven't increased in frequency at all. You see that? Category 1 hurricanes are actually a little bit less frequent than they used to be. They're not on the graph because it doesn't go below 0. And that means that overall hurricane frequency hasn't changed at all. But look what's happened to the Cat 5s, okay? They're almost 4 times more likely over just 30 years, okay? Now there's uncertainty in the data because there aren't very many Cat 5s, but that's a terrifying signal if you run an insurance company, for instance. All right, so what do you price your hurricane insurance at? All right, you actually, if the frequency of getting slammed and losing all your money is really 4 times bigger than you thought it was, you should really make it expensive, right? And so So this is the story. There are all these big hurricanes now, these just super typhoons that keep slamming it everywhere. There's just another one in the Philippines, right? So, and of course, we've got California fires. This is a figure actually from 2020. The telling point is that we could have made lots of figures from like right now, okay? And so, like every year, you can make an attributable fire graph for California, and it shouldn't be too surprising that literally hundreds and hundreds and hundreds of lawsuits have been filed using this methodology to say, look, this event that damaged me was caused by, in part by you in a way that you're responsible. There are two groups that are being sued. They're municipalities. You should have known, and you should have boosted up your infrastructure so that my house didn't get wrecked, or my grandmother didn't drown in the basement apartment in Queens. Should have known. Or it's fossil energy companies. You had a product, you knew in the late 1970s that it was dangerous, you lied about it, and now you need to pay me for my damages. Okay? None of the latter have been successful. Some of the former have. So get out your eye clickers. And the question I have for you is whether or not this is a good idea. All right, first of all, is this a good idea? To all these lawsuits, is this actually the way we're going to get to the other side? Or is this just going to complicate everything? Is it going to make everybody gun shy, fight like crazy, that sort of thing? Is it a good idea? Strategically now. I don't mean defensible morally or ethically. That's going to be the next one. And so just yes or no. Yes is A, no is B. I'm going to actually see the results in real time. Okay, that's enough. You can keep clicking if you want. Somebody that answered no, it's not a good idea. Somebody be brave. Tell me why you voted no. Okay? Yeah. Yeah, that's right. So it's in your case, it's the blame is really distributed. Turns out there are 90 extent fossil companies that put most of the CO2 in the atmosphere, so there's a group to sue. But it was humanity in general that had the demand, that argument goes, right? And so for your municipality, though, it's a little harder, right? So, I mean, if you've been telling people that climate change is a hoax and all of a sudden it comes and knocks everybody's house down, somebody might be mad at you, right? It's a little harder. You wanted to say something, yeah? Right, that's exactly right. So, it's the physician heal thyself, right? I mean, so, right, so anybody who voted yes want to defend yourself? Yeah.
So I actually agree
Yeah, so that's a great argument too, right? Okay, some of them in particular lied about it and extended the time until we had alternatives, okay? And so they're culpable for the time gap that they created, right? So this is complicated. But anyway, we're done with the lecture here, I think. I'm just going to flip through the last